Okay, so I'm just before we stop for lunch, I'm just going to talk about the multitasking system for a bit, because we've been running one program, although Mark there has actually run one program twice, run 2 copies of it, which is possible, and this is all achieved by having a multitasking system. We can actually have multiple programs running at the same time. So why do we want to do that? Well, we can have multiple functions on a machine. Typically a machine does have lots of different functions on it, so it makes sense to split it up into different sort of program functions as well. Some of those functions will have to run one after the other. Some of them might be running concurrently, where they're running in parallel, so that allows us to do that. Typically we might have a power-up sequence, which would involve our startup program we've just been looking at. After power up on the typical machine, you might want to home the axes, because a lot of times, especially these, have incremental encoders, so on power up you don't know where they are, so you have to go and find some known position to home it. We would probably want on a machine to have something that's monitoring any errors going on, and either simply reporting the errors, flashing a light, or just stopping it, or even trying to correct the machine if there have been some errors, to go through some sequence to try and perform some kind of error correction. And then the main parts of the machine itself could be split up into different things, like the main motion part of it, HMI handling, some kind of mini PLC going on where you've got some I/O being handled. So there's lots of opportunities for doing things in parallel, should you need to. And the multitasking gives us a great way to do all of that. So we can divide up tasks into something that's sort of fairly specific. Even if you have a large machine, you might have an input side of it which maybe has 3 motors on working together. That could be defined as a task that's running the input side, and a middle bit of the machine with a certain number of motors, and an output part of the machine with a certain number of motors. And you might well split it up so that one program runs the input side, one program runs the main bit in the middle, and another program runs the output side. But it's all down to particular machines, really. Error handling, we can do stuff to look for errors, and even these days where we can communicate to the servo drives, we can actually pick up error messages from the drives if you program that in, and report all that up to an HMI. Or even these days up to the cloud, so that someone on the other side of the world can see what's going on. Now our operating system is not like Windows. Windows does multitasking. You can open Word and have Outlook running, and you can have various things all running at the same time in your PC. Same in your phone. You know, your phone can be watching a YouTube video, and at the same time it's getting emails in. This is all to do with multitasking. With our system, it's designed to effectively keep running. So there's not so much error trapping in it in terms of what the multitasking does. So if you run 2 programs, the 2 programs actually will not be aware of the other one running. There's nothing in this program as it runs along. If this tries to turn a motor clockwise, and this one tries to turn the same motor anti-clockwise, they'll both do it, and they won't know the other one's doing the other. Yeah. So there's no kind of communication between the processes, unlike in Windows. If you try to in Windows try to open a serial port, I know we don't have COM ports these days, but if you try to open a COM port with one bit of software and then try to do it with another bit of software, it'd say no, you can't, that one's already in use. You know, we used to have this where our software was resident on an Allen Bradley occupied PC, because the Allen Bradley software, as soon as you start the PC, it says, right, COM port, I've got that, and it does it right from the word go. And then when we try to start Motion Perfect goes, oh, there's no COM port. But it's only because the Allen Bradley software's basically occupied it and taken over. Yeah, there's no checking like that in our controller. So 2 programs try to control the serial port, yep, they can do it. But if one sends the word hello and the other sends the word goodbye, what comes out of the serial port would be HEGO, LL, OD. It would just mash it all up because there's no controls on it. Command line, of course, is a real benefit to us. What I mean by the command line here is actually that means the entire Motion Perfect connection. So while we're running all our other programs, Motion Perfect can hook in there and can tell us what's going on and allow us to do sort of real-time debugging. All of this, when I started with Trio, was almost impossible because we only had a controller that ran one program, and if you wanted to connect the software to it, which was in DOS, you had to stop the program before you could do the connection. It would only do one thing. And now we take all this for granted. It's like I say, all of our phones, all of our PCs have this anyway. Okay, a few words. I've used the word process on the previous slide rather than task because IEC programming language, the PLC language, has taken the word task to have a specific meaning. So when you talk about a task, that's an IEC task. So a process is one of our multitasking slots that could be running BASIC, or it could be running the PLC, or it could be running, if we decide to use another language in the future, it could be running another language. Okay, I got you putting run something comma 0, something comma 1, didn't I? To run it on specific, those are called processes. And each controller has a maximum number allowed. So 0 is the first one, and then whatever the maximum is will be the top. On these, the maximum one is 9. Yeah. On the 664, the maximum is 21. Yeah. And on a lot of our high-end controllers, it's 21. On our lowest range controller, the 403, it's only 0 to 5, 6, 5. I think it's 0 to 5, is it? Because it's 6 processes. Yeah, yeah. And you can see here I've got quite a cluttered, there's a lot of programs here, and I'm running a few of them, but you can see this little triangle that appears here. If you click that, it actually shows you the process number it's running on. So you can see there I've got main running on 1, motion 1 is running on 21, and something called printer is running on 20. Okay, that's the list of different process numbers that are available on the different controllers. I think that's up to date, isn't it? I don't think there's any more. Until Fred finishes the 404, then we'll have to add that to the list. Okay, and then just going back to how we might configure things, you have one program that runs on power up, say I've called it main, could be called initialize or whatever. That then is going to be running the other program, so it runs the startup, runs some ladder logic maybe, and then runs various other different programs as needed. But the important thing is that this one called main will continue to run all the time, even if the others stop. We want this one to stay running, so you need to really write that with that in mind, so it won't suddenly stop or quit because there's some error, because it should be monitoring errors in the other programs. We can look at what's running under the directory link in this menu here. There's a processes menu, so when we look at that we can see what processes are running. It'll tell us what line number it's on, and how many percentage of the CPU it's using, which is sometimes useful. This particular picture is taken from a 664, so it's a multi-core processor. So it's actually also telling us what core it's running on. So you can see the one called main running there is taking 100% of the time on core number 2. Printer's paused and is taking 0%, and motion 1 there is sleeping, which is taking 2%. So we would pause a program like that by pressing this step button, for example. Sleeping, so what's sleeping? A sleeping program is kind of useful because it means when the program's doing not much, just waiting for something, it's giving up its processing time to other stuff. So it allows other things to run faster. Okay. And what puts a program to sleep are those 3 commands there. So either a WA with a time in milliseconds, or if you're waiting for an axis to finish, wait idle, or waiting for an axis to be loaded with a move. So those 3 there will actually put a program to sleep. Other things, though, if you put something where you're doing wait until an expression, that doesn't have the same effect. So this here, wait until something equals whatever, that does not put it to sleep. It continues to process that all the time. So it's just using up processing time, doing that expression and check. So you've got to be a little bit careful, because if you say wait idle, that puts it to sleep. If you say wait until idle, that doesn't. It's a different situation. Okay, so in the multitasking itself, we tend to run, obviously we're doing servo loops and servo control and motion. We've got to do that on a very strict time basis. So every millisecond or every servo cycle, typically a millisecond, the first thing that happens is all the servos are done and the motion is done. So all that's processed so that the next part of the move can be happening. And you'd be surprised, even if there's a 1 millisecond break in a move, you would see it. You might even hear it in the servo motor. There'd be a little tiny dink sound or knocking sound as there's a slight disjoint in the motion being processed. So it's very important that that is processed every millisecond without fail. And that's really what our system is designed to do. Now when it's finished doing the servos in motion, whatever time is left over is given to your programs, okay, in the multitasking. And obviously the more motion processing you're doing, that increases that amount of time and it reduces the amount of time given over to programs. But don't worry, it's really fast. The processors are so fast, you hardly see this effect at all. Unless you're someone, one of our Chinese customers who buys the cheapest controller and tries to do the biggest machine. In that case, they do start to run into some of these issues. You can read the amount of time taken in a servo cycle with system load for the servos and motion. So you can read that back. And generally, the more axes you put in, the higher the system load will go. And it'll peak a little bit if you do a really complex type of move. For example, launching a cam or launching a flex link or something where there's a lot of processing needed as the move starts. You'll get little peaks in system load. So momentarily it might just go up and then down again. But again, you would never see this in reality. It wouldn't cause a detrimental effect really on your programs. Now, one thing that will affect your programs a lot would be if you decide you want to close the loop much faster. Now, a 1 millisecond default there, we've got servos of motion taking, what would you say, about 15% of the total time, and the rest of it's left for the multitasking. If I go to 500 microseconds, of course, I've got to do that twice every millisecond. So now, my total time available for my basic programs is now a little less, isn't it? Because I've basically doubled up that bit, so squeeze that. So my programs, and don't forget, it's not only your programs, it's also comms over Ethernet. All that has to be processed in this part here. That's now going to run a bit slower. Now, if I go to 250, look, it really gets much worse. So when we get customers who say, oh, you know, I must close my loop at some crazy fast rate, you say, okay, fine, you can do that, but don't expect peak performance on all the other stuff, because it is going to affect it. Yeah. And there are not many real systems where you need to get down to this level. I mean, you're talking about lifting masses on, or people on hoists. Milliseconds, fast enough. They're not going to go very far in a millisecond. Their inertia. So that's one little effect of, say, increasing the servo rate. In the multitasking, we've got a concept of two process types. There's a fast one, and I've called it in the slide slow. My boss prefers it to be called level. He's decided level is a good word for the other type. So there's fast and level. You might see the reason for this. He doesn't like the word slow. Well, I can understand that. So I've got 3 programs running there. See the process numbers, 20, 21 and 19. And what's happening is that 20 and 21 are my fast ones, which are shades of grey here, these two, and then one slow process, or level process as it's known, which is that one, and then actually a quarter of that has to be given over to the system. So there's a system process running all the time, and what that's doing, it's actually doing the comms, so it's got the Ethernet stuff in it, it's got stuff, if you're running CAN bus, it's got CAN bus in it, so it's got all the stuff the system needs to be running in the background. Not the motion has its own special place, but everything else that runs in the background is in the system slot there. So that's fairly even, isn't it? So I've only got 3 programs running, but there's actually 3 places it can run every millisecond. By the way, it doesn't mean that, nothing in this means that if I've got a program written, in that time there, it will go from top to bottom of the program. We have no defined scan rates. It will simply run as many of the lines of the program as it can in that time that it's given. So if that's 25% of whatever milliseconds it is, it might run 30 lines of code. If they're very complex lines of code, it might only run 10. But that's definitely, and basically everything gets put on the stack and it carries on then. The next time it gets a processing slot, it'll continue. So what you see is the programs running continuously. What's actually happening is they're being cut up in time very, very rapidly. But we're talking about sort of average times here. So if I add a 4th program here, so I've got my 2 fast ones, remember they're the highest 2, 20 and 21, and 2 slow ones, or level ones. They have to share just one of the quarters. So my 2 fast ones always get that, and my others all have to share that one. So if I run 2 fast ones and 10 of the others, they all have to share this little slice here, which means obviously they're only going to get processed once every 10th millisecond, effectively. 1 in 10 milliseconds. So sometimes it's better not to use the fast task. If you have no reason to do this, and the only real reason for wanting a fast task, there's 2 reasons actually. One reason would be you're waiting for some kind of input to come on and you need to respond really fast. Yeah. The other reason might be that this is something to do with comms or Modbus or something, and you want that to be processed really quickly. So to give it a higher priority to allow the comms to be rapid. But if you don't want that, if that's not necessary, it's actually a better strategy to run everything on the same level as slow processes. So you can see here I've got 4 running. On the previous slide I think I had 4 running actually, didn't I? I've got 4 running there, but these are running slower. But here I've got 4 running and they're all got an equal slice. So you just equally let them all have the same level. That's why my boss wants to call it level, because they're all on the same level. So you've just got that two-tier system really. There's no difference between a program running on process 1 compared to process 7. They're running on the same level. It's only the top 2 that have any difference, and in your systems that's 8 and 9. Notice the system process always gets its slice whatever, so it carries on, doesn't share with nobody, or anybody should I say. Now we can read the processes in the terminal. If I type the word process, I'll read them all like that. And you can see here that actually it's listing not only our user programs running, so we've got startup and 2 other programs there, it's actually showing you all of the system stuff as well, which probably isn't too much interest to you, but it kind of gives you an impression of the fact, for example, nearly 5% here is being taken up by the TCP/IP server. This is for the Ethernet, and nearly 5% is being taken up by the EtherCAT on this one. Doing some processing. Something called a display manager. I have no idea what that is, apart from it might be the LED display, LCD display. MPE is the motion perfect connection, so that's taking up 5% as well. And the protocol scheduler, this is the bit that actually schedules between, no it isn't, I beg your pardon. Protocol scheduler is to do with protocols. Not sure, don't know. But it's to do with communications anyway. So as you can hear, a lot of that's to do with communications. This particular one isn't using any CAN bus, so you see the CAN bus server here is actually using 0. So you get an idea of what's going on anyway. We don't have a huge influence over this, and you know, trying to adjust things and make them run in different priorities. With some fairly expert knowledge, you can change how things will run, but it's really beyond the scope of this course. So it is possible to give like more time to this bit and less time to your user programs, but I wouldn't recommend it. It's best just to leave it to sort itself out, really. It does a fairly good job most of the time. Okay, there's the system processes. And of course the kernel bit, this is our motion processing, so that stands out on its own. That always has its own amount of running. So if we run a system with for example, if we run an EtherCAT system with say 20 axes on, you'd expect that maybe to be more like 50%, because you're running a lot more axes. Okay, the multi-core things. So our Flexix Nano and our MC6N both have a 2-core processor, and the sort of tasks are split up like this. So we've got servos of motion on 1 core, and all of our basic programs I was just talking about actually run on their own core. So in this case, because it's got 2 processor cores, as we increase the number of axes on here, and this goes up, it doesn't have any effect on that. So that's the benefit of having 2 cores. This bit called system tasks here, we can allocate that to a number of different things. That's kind of variable. One of the things we sometimes do, we've done this for a customer recently, is we've allocated all the Ethernet stuff into here, so it speeds up his Ethernet comms, because he was trying to send so much data in a short time to us. So we can manipulate this bit, but that bit there is the same as it is in the single core. Now the 4-core one, if we go to that, then we end up with obviously 4 cores, and what happens there is we put the system processor in its own core, so that's doing all the Ethernet and all the other stuff, servos of motion in a core, and then our user programs are split between 2 cores. And what happens there is that the fast tasks are allocated. You have 1 fast task in here and 1 in there, and then all of the others share some remaining time in both of those. So if you think of if you had a fast task and 2 fast tasks and 2 slow ones, or 4 slow ones say, the fast tasks would take 50% of each of those, and then the slow ones would share the remaining 50% of each. And again, it improves performance, of course, at a price. And there's a screenshot of doing the process command on a multi-core controller. So you can see the servo scheduler is on 1, so that's the system task, is it? No. Yeah, sorry. Yeah, so the servo, this is the motion bit. Servo scheduler is the most motion bit, so that's running on 1 core. Then all the system stuff's running on core 0, and then the user programs are running on 3 and 2. So how does that affect us? You write programs and you run them, and it just runs them. So normally everything you do, the processor's fast enough for you not to worry about anything I've just told you. But we do run in occasionally to situations where users are trying to get an awful lot out of the controller, and then you have to start thinking about exactly how these tasks are running with each other. When you write a program, you want it to move stuff, so you will be obviously writing a program that does moves. What happens when you get to a move in the program is that it's transferred into the motion part. So when you get to the command move, it will actually go into here. You'll see it appear in that part there. Instead of idle, it would say move or forward or whatever the command is. And once it's in there, it's using the preset parameters that you've put in there, okay, which we've already been setting up some gains, for example. So the motion part runs really on its own, completely, almost like it's a separate device in some ways. So when your program comes down and does a move, so you come down here, set the speed, actual, do a move there, that move initially goes into the program's own buffer, and in there it is then signalled to the motion system to say, hey, I've got a move for you. And then the motion system will go, okay, I'm free, that axis is not doing anything, give me the move. And the move goes across there, first into something called the next move buffer. And then if the main buffer, move buffer is available, it'll just go straight into there, and then it starts to run. So this bit here, this velocity profile unit, is the bit that does the actual motion. And then the servo control part of it that we've been looking at tuning, that takes these millisecond by millisecond, a new demand position goes into here and is used to control the actual position of the motor. And that's basically the sequence. So the two boxes here, the one on the right hand side and the middle one, what's called deterministic, they're run in the main kernel once per millisecond, and then the bit that's running the basic, we have no kind of specification of exactly how many lines of code it will run. It just runs quite fast. But we can never actually say how long it will take to run those 4 lines of code. It is quite variable, but let me assure you, it's fast enough. You know, it'll run far quicker than any machine that you're trying to control. Any questions about all of that? It's a little bit technical.
Actually, we had experience about the application. They called transfer machine.
Okay.
The transfer machine use several multi-axis parts. For example, 2 axis do the drilling.
Mm-hmm.
The next station, actually the station just moving, and the work is moving between, exchanging the position between the different stations.
Mm-hmm.
And the next station do some tapping, for example.
Yeah, yeah.
And the next station do some engraving, for example. So the same part, exchanging stations into the machine. And then finally, the final piece go out of the machine, unloading by robot or something like that.
Yeah, yeah.
So in that application, they use something like maximum 21 axis, 22 axis in the same machine, in different multi-axis stations.
Yes.
So in that cases, can we use, for example, for 21 axis, which kind of controller can be useful to use in that machine with the minimum price, I mean?
Well, the Flex 6 should run 21 axes.
Okay.
Yeah. On the EtherCAT, that should work.
EtherCAT, yeah.
Yeah. I would imagine you're not going to have, you've got 21 axes, but you've not got 21 workstations around that. So your number of programs you need to run, I would suggest you're running 1 program for each action, each station.
Yeah.
But maybe there's 10 stations.
Yeah, something like
some
that.
have 1 axis, some have 2 axes, whatever.
Yeah. Exactly.
And everything coordinated by 1 main program that's doing the main sort of transfer time.
Yeah, they're running at the same time, but should be in the different tasks like that.
Yeah. No, that would.
So the Flex 6 Nano.
Flex 6 Nano would do that, I would have thought. It's really the number of axes that governs what controller you pick. So not necessarily the number of workstations or whatever. It's the number of axes.
Okay.
Yeah.